I'd like to welcome fellows and visitors to the fifth discussion meeting of the current session of the Royal Statistical Society. So this online format follows closely our traditional red paper meeting. However, with one big difference, we're all connecting from home. So please don't worry about unplanned connection problems or domestic issues. These things happen. If you do have a problem, one of the speakers, then maybe let us know by email, which we'll be monitoring. And, you know, these things happen. If you do experience technical problems, please use the support chat box to outline your query and someone will help sort it out. Please don't just come on the microphone and start speaking. Use the chat box. I have to tell you that the meeting is going to be recorded and posted on YouTube afterwards with the slides. If you do object to this, please can you make a note in the chat box to the support people so that they can edit out anything that you might say. Please, only presenters today will be using video. We ask everyone, unless speaking, to please keep your microphone muted also. So generally, only the person speaking should be using video and microphone. If you are going to speak later as one of the discussants, please try and use a headset connected to the audio port to ensure that there's good quality video and audio, remembering we're being recorded. Everyone attending the meeting is invited and openly encouraged to contribute to the discussion of the paper. In the discussion section at the end, comments can be made that will take place after all the presentations have been made. So please do not attempt to ask a question during any of the presentations or the proposing or the seconding. If you want to say something, there will be opportunity in the discussion later to do so. If you wish to contribute to the discussion and you haven't let us know in advance, please leave a message again in the support chat box to say that you wish to contribute to the discussion. And you can do this at any time. Later on, when we get to the discussion section, I will issue some requests for extra discussants to see if anybody else wishes to discuss. And you can raise your hand using the mechanism in Teams if you wish also. Later on, when I invite you to speak, if you want to speak, you'll need, of course, to unmute your audio. It's really useful for us if you can state your name and your affiliation so that we can follow up with you afterwards. And you will have 5 minutes only to make a comment in the discussion section. So once again, welcome. This will be, I think, the last discussion meeting of 2020. An eventful year for many reasons, but particularly because we have a wonderful paper tonight, Gaussian Differential Privacy by Jinshuo Dong, Aaron Roth, and Weijie Su, all from the University of Pennsylvania in Philadelphia in the USA. So I call on the authors now to begin their presentation of their paper, bearing in mind the time that we have for presentation. Thank you.
So first of all, let me, it's really our great honor to have the discussion meeting for our paper. So this is really a great privilege, and thank everybody for coming. So let's start. So modern technologies have facilitated our daily life in a great manner. So we can now go shopping online and socialize with our friends, sharing our stories, and we can also even attend research activities online. However, that comes with a price. The price is that we might lose our privacy. So government agencies and the big companies, essentially, they can have access of our personal data. And in the worst case, they can leverage our personal data in their hands for some adversarial use, right? So then how can we protect our privacy? A simple solution can be, for example, delete our names, make our data set anonymous. So this example, actually, Jinshuo gave this example in his demo 1 hour ago. This is a Netflix example. You are required to ask to predict the rating. Some rating are missing, rating from 1 to 5. And although the user's name are already deleted, however, the situation is that in the modern times, a single individual can appear in multiple data sets. So you can appear in the Netflix example and also in some public data sets. a 2006 paper showing that by relating two data sets, it's possible to identify some users. Okay, so as a result, the second Netflix competition was canceled due to a lawsuit against it. And then, is it possible to protect privacy? Is it possible to only release the summary statistics, meaning that you just release the average of a number or a vector from your data set? Unfortunately, this is also not the case in general. For example, due to so a 2008 paper shows that releasing the minor allele frequencies of a data set, essentially it's just the sample mean, also cannot be private. Okay, this example also was discussed in detail by Jinshuo in his demo. So is this really the end of privacy? And so the good news came in 2006, where 4 computer scientists, Cynthia Dwork, McSheffey, Esseen, and Smith introduced differential privacy. So in retrospect, now we realize that differential privacy actually has a strong connection to something that we statisticians love most, hypothesis testing. So this connection was made in 2010 by Lev Weissman and Shu Henzhou. And this connection will be elaborated a lot. Actually, the connection between differential privacy and the hypothesis testing will serve as the foundation, as a main motivation for our work. So now let's have the setup for differential privacy. So in differential privacy, you deal with a data set that every statisticians are very familiar with, a data set. So every row corresponds to an individual, and every column can be some features. Some features can be very sensitive, for example, like salary, right? Most people won't like their salary be open known to the public. So have the data set, and in differential privacy, there's another concept called a mechanism. But actually, this is just an algorithm. The output of the algorithm is the only thing you can see. In this example, the algorithm can be something like this, can be the average of the salary of the people in the data set. But in order to protect privacy, we will add some noise. So this can be an example of a mechanism. So now let's introduce another important concept of neighboring data sets. So in differential privacy, 2 data sets are called neighboring if they are basically identical, except for the last individual. For example, in this case, Bob, Charlie, and Dave are known to be in the data set. The only one who is not certain is Alice or Annie. We're not sure whether it's Alice or Annie in the data set. And then we can do a hypothesis testing. So now can be so Alice is in the data set, and alternative can be Annie in the data set. So how can we perform the hypothesis testing? It's based on the output of the mechanism M. Okay, so the output of M is the only information we have in our hand. So intuitively, if the hypothesis testing problem is difficult, meaning that it's difficult to tell apart H0 and H1, then it's hard for us to break the privacy of Alice and Annie, right? So privacy is preserved to a good extent. So this intuition, very simple, right? This intuition actually underlines the essence of differential privacy. So differential privacy now has been growing really big over the years. And so it has been incorporated by many big companies, giants including Google, Apple, Microsoft. So actually, do you see this very tiny screenshots? This is from my iPhone. So I was upgrading my iOS on my iPhone, and it asked me to upload it said that they will use differential privacy. It's a little bit, it's very tiny to you, right? The yellow in yellow text. They will use differential privacy to analyze the data stored on iCloud. So this makes me personally very safe when I use iPhone. And so this year, there's a census given by US Bureau and Census Bureau, and they also use the differential privacy in many of their summary statistics. So 3 years ago, the Goldie Prize went to the 4 computer scientists who proposed differential privacy. So what's new in our talk? So I have given a background. So in the following, I will introduce the concept of our new definition, a privacy. And later, Jinshuo will discuss in detail all the properties of this new definition. So this is joint work with Aaron Roth. So Aaron was Jinshuo's former advisor at Penn. He is a professor at Penn, and so early this year he got promoted to full professor, and good for him. So now let's make a comparison between our talk, this talk, and the epsilon delta differential privacy that was proposed by Cynthia about a decade ago. So let's first make a comparison. So this is the left is new, is something new, where we call it f-differential privacy. On the right is something old. And the first is the similarity. The similarity is that so both notions are using the hypothesis testing interpretation of differential privacy. Okay, so this is the same thing. And now comes the difference. The first difference is that, as you will see in our definition in a moment, so we use F1, type 1 and type 2 errors especially the trade-off between the two errors to describe the discrepancy between the two hypotheses, the null and the alternative. And in the older notion, epsilon delta, they use the worst case likelihood ratio to measure the discrepancy difference between the two hypotheses. And another difference comes in the parameter. So we use the functional parameter, which maps the unit interval 0, 1 to itself. And in epsilon delta, they use epsilon delta 2 parameters to measure as their parameters. So in our notion, adding Gaussian noise makes it's the most typical way to achieve privacy. So in epsilon delta, especially when delta is 0, the pure differential privacy when delta is 0 is called pure differential privacy. Then adding Laplace noise is the typical way to achieve privacy. So now let's define this notion. To give this notion, first of all, we need to introduce the concept of trade-off functions. So trade-off functions are very easy to introduce, especially to statisticians. So we have two hypotheses. Okay, as early in our setup, the null is that the true data set is S, the alternative is S prime. And now let's use P and Q to denote the probability distributions. So P is the probability distribution of the output of the algorithm if the underlying truth is null. Okay, if Alice is in the data set, then the distribution of M, the mechanism, is P. And if this is any in the alternative, then the distribution is Q. Then for any rejection rule, we can define the type 1 error and type 2 error. So type 1 error is just the probability that I mistakenly reject the null, but however, the truth is null, right? So P is the truth on the taken probability. So alternative is the probability. This is type 2 error. Type 2 error is that although the truth is that alternative is true, but I mistakenly accept the null. Okay, so this is the probability denoted by beta. Now we can define this so-called trade-off function. So trade-off function, first of all, is a function defined on the unit interval 0, 1, and the map unit interval 0, 1 to itself 0, 1. So this always depends on two distributions P and Q. So for any alpha between 0 and 1, and the trade-off function is simply the minimum type 2 error, okay, minimum type 2 error over all rejection rules, such that the level that its type 1 error is controlled at alpha, okay, controlled at alpha. So alpha here can be 0 and 1, so this is a function of alpha. And given due to the Lemon-Pearson lemma, we know that the infiniment can be achieved by using the lateral ratio test. In some cases, you might use maybe need to use randomization. So, and now let's define this FDP. So we call an algorithm M is f-differential private if the trade-off function between the data set S and another data set S prime, and they are neighboring, such that the trade-off function is always going to be larger than or equal to f for any value alpha between 0 and 1, for any alpha 0 and 1. Okay, and here the randomness, as you see in the beginning, we always will add some noise or introduce some randomization in the algorithm. So the randomness comes from the algorithm M, not from the data set. S and S prime are always fixed, okay, for any neighboring data sets. So this means that if f is given by the trade-off function between p and q, then to distinguish between Alice and Annie is at least as difficult as telling apart p and q. Okay, if p and q are very close to each other, then the privacy is somehow it's strong, right? Otherwise, it's easier to tell apart. So this is related to the hypothesis testing region given by the author 3 years ago. So now let's make a connection between epsilon delta and the FDP. So first, the message is very simple. Epsilon delta dp actually is included as a special case of our FDP. So first, let's record that what is epsilon delta dp. So epsilon delta dp is just this line, define this line. So roughly speaking, for any measurable data set, if the underlying truth is S prime, and if the underlying truth is S, then the two probabilities should be close to each other in terms of epsilon delta. If epsilon delta are small, then these two probabilities are close to each other. So a result due to Larry Weissman and Jinshuo Zhou about 10 years ago. Of course, they didn't use the F language. Now let's translate their result in our FDP language. And then their result essentially saying that a method M is epsilon delta dp if and only if this is also FDP. And this F is given by this line. This is a little bit weird, but let me explain to you. So this is essentially a piecewise linear function. So it consists of 4 segments. And this is the intercept, meaning that this part is perfectly aligned with the y-axis. And now, for starting this part, it has slope minus e to epsilon. So this part has slope minus e to the minus epsilon. And here, this is also delta. So they are all, it's symmetric with respect to this 45-degree line. However, from a high-level perspective, why should a trade-off function should be consist of 4 segments? A little bit ad hoc, right? Intuitively, this can be any smooth function. And another issue with epsilon delta dp is that, and here with probability delta, we have nothing to say about this algorithm. So meaning that with probability delta, arbitrary worst case can happen in this case. So now maybe F is quite too general. And now let's introduce a single parameter family privacy. So this is the Gaussian differential privacy, in short called GDP. So GDP is simply the trade-off function between the stand normal, this stand normal, and stand normal with mean shift mu. So mu can be always assumed to be larger than or equal to 0. And this trade-off function actually admits a closed form expression, where phi is the CDF of the stand normal. Very simple, closed form. And now we can define the GDP definition, give the GDP definition. So a mechanism is called mu GDP if the trade-off function between any neighboring data sets, S and S prime, is always larger than or equal to the trade-off function G mu. So this is a single parameter family. And as we know, due to the linear discriminant analysis, in the multivariate Gaussian case, as long as the covariance is the same, then a mean shift between 2 Gaussians can always be translated to a one-dimensional Gaussian testing problem, right? So in this, so this shows that a single family is parameter mu is enough to deal with the general case. So this is will be the most important family in FDP definitions due to a central limit theorem phenomenon, and this part will be introduced by Jinshuo in detail in his second part. So how can we interpret mu in GDP? First, let's plot the trade-off function for different mu. And so here, this is the 45-degree line, and so the perfect privacy. When mu is half, it's here. Mu is 1, it's there. So mu is 3, due to the 3 sigma principle, we know that the privacy is not that much, right? And when mu is 6, then everything is gone. So roughly speaking, if mu is smaller than 1, yeah, so this is somehow reasonably private. When mu is larger than 6, no privacy at all. So now let's briefly introduce how can we achieve privacy. So roughly speaking, add noise. So you are the user and this is data set. You ask, so this is your statistic theta. So I apologize, theta here is the statistic, not a parameter. And then what you get, in order to make it's private, it's just some noise to your statistic. So here, this is how much noise do you add really depends on the sensitivity. So sensitivity of a statistic is defined as the maximum perturbation you will have for any neighboring data sets, S and S prime are neighboring. And then for Gaussian mechanism, we can make it private by just adding Gaussian noise. So this is your statistic at the Gaussian noise. And how much Gaussian noise do you add? It's given by this relationship. So mu is equal to the sensitivity divided by sigma. So if mu is large, then you should add small. You can add small noise, right? Because in this case, you can tolerate more privacy loss. If mu is large, then mu is small, then you should add more noise. Sigma should be large. And then what's more important is that here, even from the FDP perspective, and the trade-off function of the Gaussian mechanism is exactly equal to the trade-off function of Gaussian noise. So this suggests that Gaussian mechanism is to GDP is just like the Laplace mechanism to the epsilon 0 dp. But however, its Laplace mechanism is really perfect for epsilon dp. So here we want to argue that actually it's not the case. So pure differential privacy can be guaranteed by Laplace noise in this way. Just add Laplace noise to your statistic. So Laplace noise here is given by this density. It's just double exponential distribution. So if lambda is large, then lambda here is given by the sensitivity divided by epsilon. However, if you look from the diagram, the trade-off function of the Laplace noise here is given by the blue line. But however, the trade-off function given by epsilon 0 is given by this red line. There is no perfect agreement. So this means that Laplace mechanism might not be that perfect for pure differential privacy. So if we go beyond Laplace, talk about Gaussian, the situation is that even Gaussian noise is not epsilon 0 dp. So this motivates epsilon delta dp. We need to introduce some slackness delta. But however, the issue remains. The issue is that the loss is still there. The loss might be even larger between the epsilon delta dp trade-off function, the Gaussian trade-off function. Okay, so my part is done, and the next Jinshuo will introduce the detailed properties of our FDP definitions.
Hopefully not only. Okay, so Weijie already told us if we generalize epsilon delta dp to f dp and then specialize to GDP, then we get a really clean analysis for the fundamental Gaussian mechanism. He also did a little bit of a spoiler, but let me say this. GDP is important for more reasons, not just because we statisticians have a fetish for Gauss. Actually, our fetish for normal distribution doesn't come from thin air. It comes from the central limit theory. Okay, so that's what is promised by Weijie. Our fetish for GDP also comes from a central limit theorem in the privacy context. So in the end, everything will converge to GDP via the central limit theorem. To introduce that and to have some real application, in particular to the private version of stochastic gradient descent, which is the go-to method for machine learning in this time. We need a toolbox, which includes the following. There are precision tools, the composition and subsampling. They're both involved in SGD, and in the paper we also mentioned group privacy and also post-processing. We have some comments and nice things to say about it, but okay. So from these tools, you can see that epsilon delta dp is basically an approximation, and the approximation makes things complicated. Well, on the other hand, f-dp and gdp makes they're precise and they simplify things. So that's what you can. I hope that's what you can observe from our theorems. For this talk, we'll focus on the first two tools, composition and subsampling, because they are crucial in SGD. Let me briefly tell you what they are. Composition is useful when releasing several statistics, okay? Or when the algorithm is iterative, such as gradient descent or stochastic gradient descent. Well, in vanilla gradient descent, the gradient is evaluated on all data points and then averaged, right? So the gradient can also be considered as a statistics of the data set. So that's how they are connected. And subsampling is a useful technique when, because privacy is the bottleneck rather than the statistical efficiency. For example, when you estimate the gradient, you don't have to estimate to the full accuracy. You just need a somewhat correct direction. So you don't need to use the whole sample size. You can sacrifice a little bit of statistical efficiency and try to increase privacy. Well, I mean, mini batch SGD is not invented for that, but it happens to bring us privacy because of its mini batch. Okay, so that brings down the statistical efficiency, but improves privacy. SGD involves both of the components. Okay, let me first start with composition. So recall that the typical example is some user, potentially bad guy, but also potentially a good analysis, ask us to evaluate statistics, for example, sample mean, and then we are going to return with some noise to protect privacy. So what if this query, this statistic is high dimensional? For example, using the previous table, the statistic can be first average salary and the second average age. Well, that is straightforward. We can simply add the noise to each of the coordinates. Okay. Suppose each coordinate is dp. Let's say GDP. So for each coordinate, testing whether you're in there is like testing to one-dimensional Gaussian. Okay. And well, what about the whole thing? So because it's often the case that we are going to add fresh noise, which is independent noise. So this mechanism is the composition of individual one-dimensional mechanisms, and it's more like a product than a function composition. And we'll see that later as well. Like product distributions really or product it measures already pops up in the theory. Let's simplify things and consider composition of GDP. Suppose the ith coordinate is mu I GDP, then we can conclude that the whole thing is mu GDP, where mu is simply the two norm of all of the mu's, mu i's. Okay, so that's the claim. Let me explain why that is true. It's actually very simple. The intuition is because we have independent and fresh noise, then for each coordinate is mu I GDP. So for the first coordinate, it's as if we are testing normal 0, 1 and normal mu 1, 1. Okay, so that's the definition of GDP. For the second coordinate, it's like testing normal 0, 1, normal mu 2, 1, and so on and so forth. So join this together, it's like we are testing a high-dimensional normal and versus a different high-dimensional normal. So the first one is going to normal 0 identity. So the mean is 0 vector. And the second is normal mu vector in the identity. Okay, so this argument can be made precise. So as Weijie mentioned, if we have two high-dimensional Gaussian and we are trying to discriminate them, and then the following figure for LDA, linear discriminant analysis, is helpful. So what you actually, I need to apologize for not being able to make this figure on my own. The major difference with our case is that we have spherical Gaussian. Okay, and the left panel and the right panel is to distinguish when they are not spherical. You should do something different for LDA. But we have spherical Gaussians, so we can simply look at this one. The best thing to do is to project the two normals, two spherical Gaussians, to this axis, where it is the direction that connects the two means. Okay, that is optimal because we have spherical Gaussian. When you project to that axis, we have one-dimensional Gaussian, where the mean shift becomes the distance between the mean, which is the length of this vector. So that is how we reduce. So first, we identify composition of GDP with high-dimensional Gaussian, and then we project it to one dimension. So we are back in the one-dimensional case where the mean shift is this much. So is that clear? So for composition of GDP, we have a nice formula. But in contrast, if you take the epsilon delta perspective, then you have, well, it's some formula, but to me, it's less easy to understand. If each coordinate is epsilon delta dp, then the whole thing is this much dp, where the expression you can find here. Okay. The formula, so remember that we don't have to assume each step has the same parameter for GDP. But if you assume inhomogeneous parameters for each step, epsilon I delta I dp, then the formula gets very, very long. It's, long enough that I don't want to show you. So this might be a curious puzzle for us. Okay, let's be even more general. So in order to show you that everything converges in the central limit theorem to GDP, you need to consider the composition of f-dp. So we have already mentioned this point. Composition corresponds to product measure. Let me make it more concrete. So let's start with a simple case. There are only two mechanisms. We're only releasing two statistics. One is f dp, and the second is g dp. So this is different from the letter g, it's a function g. Then the composition, or we say it's simply the product of the two mechanisms. We just release the results as a whole. And this thing is f times g dp. This product, I need to define it. So how do we define this thing? So first, we express f as trade-off function of two distributions p and q. Okay. Do the same for g. G equals trade-off of p prime q prime, and then we can form the product measure, p times p prime, q times q prime, and then f times g is the trade-off function of that. Okay, so is that clear? Okay, no question. Let me tell you that, well, in this definition, you first take pq and p prime q prime, and then you try to define something independent of it, only depends on f and g. It turns out this definition is well defined. So if I choose one pq, you choose some other p1 q1, we're going to end up with the same function. So that's nice. And also, it's quite easy to see that f times g is equal to g times f, because swapping the coordinate doesn't change anything. So the product is commutative, is also associative, and I guess we should mention that the x plus y equals 1 line corresponds to perfect gravity, and that corresponds to the two distributions p equals q. Where the only thing you can do is random guessing. So you have type 1 plus type 2 error equals 1. Okay, so if you times that, then you get the same thing. So there's a sort of identity. Anyway, so it's not too important. Okay, well, we also like to mention that this not only work for adding fractionals, it also works for adaptive composition as well. The example is gradient descent, stochastic gradient descent. Suppose the ith gradient step is fi dp, because the next gradient step also depends on where you go in the previous gradient step. So it's not going to be completely fresh noise. But the theorem also applies. The whole training process is going to be f1 times 2 fn dp. Okay, it looks like this is something we want to study. If we can figure it out, we get a good idea of, say, iterative algorithm, and also releasing multiple private statistics. So let's start with a simple case. What if all fi are epsilon delta, the piecewise linear function? I'll show you the picture next slide. For some epsilon delta. So I'm saying that all of them are equal to the same thing, okay? For some epsilon delta. And in particular, we can set delta to be 0 and consider this thing. Okay? So it means this thing times itself in the above sense n times. Okay, let me show you the picture. When n equals 1, that's the picture you have seen. It's a piecewise linear function. Delta equals 0, so we don't have the intercept. And now let's increase n by 1. You have one more segment, and then n equals 3. One more, 4, 5, and then when n equals 10. Then let's look at n equals 20. Clearly, it's converging to something, and if you pay attention, you can tell that it's converging to some GDP function. Okay, that looks nice. What we observe is the following. We have been considering this function, right? It converges to GDP function. Remember that this is the trade-off function between normal 0 and normal 1, 1. I didn't tell you that I said epsilon to be 1 over square root of n. So in the last here is 1 over square root of 20. We'll talk about that later. So more generally, we show that This thing that we are interested in for iterative algorithm, multiple private statistics, it converges to G1, 1 GDP. Okay, if these things are scaled correctly. Well, let's worry about the precise condition later, and try to interpret this conclusion. The interpretation is each step F1 measures a small privacy leak in each step. Okay, so small privacy leaks accumulate or compose to GDP. So that's what this thing says. The condition is if they are scaled correctly. So why do we have? So why do we call it a central limit theorem? Let's compare it with the random variable CLT. It's saying that small random effects, basically just random variables, sum up together. They accumulate to Gaussian if they are scaled correctly. Okay, we really need this condition because we need to divide by the standard deviation so that it converges to the standard normal. Think about this G1 as the standard normal counterpart. We also need that none of the random effects dominate the others. Otherwise, it's just going to be this random effect itself is not going to accumulate to anything interesting. So we also have similar conditions like F1, they're roughly equally private. It's not just all of the privacy loss happens here and the other things are small. In that case, we're not going to observe central limit theorem to GDP. Okay, let me be more specific about this formal theorem. So the theorem, so the scaled correctly conditions are just some moment conditions. I'm not going to try to hide it in the mystery. These conditions are basically computing do you see the slides? Yeah. Looks like okay. Let me proceed. So these conditions are basically computing the moments of the log likelihood ratio. So we already reviewed the close connection with Neyman Pearson, so it's not very surprising here. And in the precise statement, triangular array is needed because these are independent. You can think of it as independent, but not IID random variables. And there's also a Balle Esseen version saying roughly that the product is roughly order 1 over square root of n away from GDP function. But hearing that, maybe you wonder, let me show you the picture again. So the Balle Esseen version tells us this is 1 of square root of n convergence. But the n is only 20. So really, 1 over square root of n convergence? Well, it turns out we can improve on the Balle Esseen version. Again, this is the correct scaling. Okay? So this guarantees the previous condition, like these conditions. Okay, so let's not get into that. We can show that what we already observed, this thing converges to this thing. The convergence rate is 1 over n. So the metric is, well, I would like to say it's a function norm, like L infinity, but it turns out it's the Levy metric, where it's often useful for comparing CDFs. And simulation shows this constant is also very good. It's 0.1 over n, so that makes sense. 0.1 over 20 is like looks like explains this picture. Right? And the reason we have the improvement is it comes from a smoothing effect from the randomization in optimal test. For Neyman Pearson, you sometimes need to randomize. So that's the smoothing effect. Okay, it also has the flavor of continuity correction. Let me remind you what it is. We all know that we can use Gaussian to approximate binomial. Suppose we have a random variable binomial random variable x and a Gaussian y with the same mean and variance. So so they should have similar CDF. But it's better to approximate this CDF x less than 8 by not y less than 8, but y less than 8.5. So these two things have to have similar behavior, similar flavor. Okay, from this picture, what is the high-level message? I think it's clearer if you add one more curve, which is the optimal epsilon delta curve for the composition. So if you want to conclude epsilon delta about this composition, you need to put a lower bound on it, right? But the optimal lower bound looks like this. Delta is typically small, so that's why we cannot have it close to the original curve. Okay, I should mention that so GDP is function is tangent to this two axes. Okay, so this looks to me that concluding epsilon delta is like trimming a foot to fit the shoe. So we already have a perfect shoe here. Why bother converting it to epsilon delta? So in our opinion, GDP is the perfect shoe for composition. And then the next step, I'm guessing I'm running out of time. So how much time do I have? Maybe 5 minutes or?
Yeah, 5 minutes is fine.
Okay, I'll try to. Okay, so what is the idea of subsampling? The motivation is using a subsample offers more privacy than using the full data. So for example, let's set P to be 1/2, using 1/2 of the data to run the algorithm. It means, random half of the data. Then with half probability, you're in the data set and you get the original privacy. Okay, but with half probability, you're not in the data set. You're not even involved in the computation. So you get perfect privacy. Okay, so originally, if we have 2 GDP, then the perfect privacy corresponds to the parameter being 0. So do we get 1 GDP using half of the data? Well, it turns out it's no, but very close. So let's first average. So we can see that there's a flavor of averaging original and perfect privacy, right? So suppose the gray line is the original privacy, and we argue that this dashed line is the perfect privacy. We average that and get the blue curve. But that is not officially what we can conclude, because so remember that we have the null and alternative hypothesis D and D prime. But these two are symmetric, so we in principle can swap them and get the same result. But when you swap null and alternative type 1 and type 2 errors also switches, and this the two axes switches. So we get okay. So this is some notation. So we get some this record by switching the x and y axis. And this corresponds to the inverse function. So how do we conclude something like symmetric? It turns out the right way is to take the worst case of the two, take the minimum of the two. And but convexity is something that we want to preserve, so we find the largest convex lower bound of the minimum. So we simply connect these two dots and form the black function. So that is obtained by symmetrizing the convex combination. Okay, and we actually have the theorem. If M is f-dp using all samples, then it is like the symmetrized version dp using a p fraction of the samples, where this blue line is the convex combination of the original privacy and the perfect privacy. Okay, it's I think it's pretty nice and clean. But in contrast, well, there's not that much of contrast here. For epsilon delta, you just need to work out the expression. We have a similar theorem, and well, if we plot it, then let's suppose originally we have epsilon delta. Okay, that's the gray line. After the combination, we have the red one, our result. It's not too different from the epsilon delta result, which is stated here. That's the blue line. It's the same here and here, but very different in the middle of the region. So, like if you care about what is the smallest possible type 1 plus type 2 error, then our result improved it by a lot. The shaded area is quite large. Okay. Let me briefly go over, show you why SGD is related to that. So the vanilla SGD is, okay, we sample a mini batch from the whole data set, and then compute the gradient from this mini batch, and then take the gradient step and then iterate over and over. This is in principle not DP. How to privatize it? It's actually very simple. You just add a step that perturbs the gradient. Okay, perturb the gradient with the Gaussian noise. There's actually a clipping step to control the sensitivity, but that's for experts. If you want a detail, you can check out our paper, right? Any paper explaining private SGD. Okay, so the analysis is because we have a loop, it's an iterative algorithm, so we have a composition. Okay, so it's a composition of gradient steps. So for each step, because we take the mini batch, we are using the subsample, right? Only part of the sample. And perturbing the gradient is the Gaussian mechanism, just add Gaussian noise, right? So in principle, noisy SVD or private SVD is a composition of subsample Gaussian mechanism. So if we can work out, I didn't tell you how to work out. We know how to compose Gaussian mechanism, but we don't know composition of subsample Gaussian mechanism yet. But in principle, we can use the central limit theorem and derive the specific one for private SVD. Okay, so this thing goes to the limit is when the steps goes to infinity, and okay, so the mini batch ratio also has to go to 0. Anyway, with the parameters, we can compute the final GDP parameter, which is mu. It's a simple expression. In contrast, if you use some other tools, for example, the one being employed in TensorFlow privacy, it has to evaluate many numerical integrals. So ideally, it can compute many. So that involves a lot of computation. Here, let me, hopefully I'm not overtime for too much. I only have 2 more slides. So this is the MNIST result. We are plotting the trade-off functions of 2 things. One is the privacy conclusion of, so we are plotting the privacy conclusion of the same algorithm, achieving the same accuracy with the same parameters. With our CLT, you get this red one. It's very close to the perfect privacy, x plus y equals 1. But using the previously employed moment accountant method, you're going to conclude with the blue dashed one. It's Well, the type 1, type 2 error is close to 0, so I think it's hard to say there's any premise. Okay, so our code is also available at TensorFlow. Check out this diagram. So here comes my conclusion. I put a few plots in the footers here. So these are the things I hope you can remember. Everything converges to PDP by CLT, and this is how fast it converges. You can check out the code here, read my blog here, or follow the three of us on Twitter. Okay, I'll put it here and questions or discussion.
Okay, yeah, thank you very much. I'd first like to call on Borja Balle Pigem from DeepMind to propose the vote of thanks.
I want to start by thanking the authors for a wonderful paper and a fantastic presentation, and also the organizers for giving me the opportunity to propose the vote of thanks. My job is to praise the paper, so I'm going to start by praising the paper at a very high level. And to do that, I think I should first probably recall what are the properties that we expect from a useful definition of algorithmic privacy. So there's many properties that we expect, but the main three that I want to highlight here is that we want the definition to provide strong privacy in the sense that it avoids the pitfalls and heuristic and syntactic definitions that we've seen fail over and over in the past. We want the definition to be modular and tight in the sense that if we want to analyze a complex algorithm under the given definition, we can do so by analyzing the building blocks that go into the algorithm and compose these individual analyses in a tight way in the numeric sense. And finally, we want the definition to be interpretable in the sense that we want decision makers and like policymakers and other types of stakeholders to be able to look at an application and interpret the parameters of the definition and then be able to specify what parameters should we use for that particular definition. So if we look at these properties and we try to compare different flavors of differential privacy under these requirements of being strong, being modular and tight, where here I'm breaking it down by different properties that we want, like being able to analyze the Gaussian mechanism, composition and subsampling, and finally being interpretable, and here mostly in the sense of hypothesis testing. One thing that we see in this high-level table is that Gaussian DP doesn't by itself, I guess, like offer new things in the sense that it has properties that we have seen in all the definitions in the literature before. But what is really noteworthy is that, at least to the best of my knowledge, it is the first definition that satisfies all the properties at the same time, which I think is an amazing achievement. So I could probably like spend a lot of time talking about each individual square of this table, but in the interest of time, where I want to focus my presentation on is on the analysis of noisy SGD under Gaussian differential privacy, which basically boils down to the modularity and tightness property, and also because this algorithm is kind of the state of the art for privacy preserving machine learning right now. So in the context of this algorithm, if we look at the plots that we find in the paper and that we also saw in the presentation a couple of minutes ago, the first thing that we observe is that there's definitely like a huge gap between the red lines, which are the privacy guarantees under GDP when we use the CLT to analyze noisy SGD. That's a mouthful, sorry. And the blue lines, which are what we get out of the, say, classical or state-of-the-art analysis for noisy SGD that doesn't use GDP. And I use noisy SGD all the time, so I was trying to understand why this gap is so big. And to understand that, I think we need to look at what, like how the blue curves are computed. So as I was saying, these blue curves come from the moments accountant, which is basically like some instantiation of Rayleigh differential privacy that is very specialized to noisy SGD, in the sense that it's specialized to Gaussian noise and some types of subsampling and so on. So when we think about this, we know that Rayleigh differential privacy gives us like tight composition and tight analysis of the Gaussian mechanism. So if there's a big slack here, it might come from other properties. It might come from subsampling. It might come from how we convert Rayleigh differential privacy to epsilon delta differential privacy, or it might come from how we convert epsilon delta dp to a hypothesis testing interpretation, or probably from all of these. So one thing that I noticed is that if we look at this last property, these blue curves are computed by taking the epsilon and delta that we get out of the moments accountant for a fixed delta and applying this formula that we've seen earlier. But noisy SGD, and this is also true for many other algorithms, we actually know how to produce epsilons for many different deltas, not for a single delta. So what I wanted to do is try to understand if there's any slack in this conversion, in this last step on how we get the red curve. And basically to do that, what we can do is we can think of a conversion between a whole curve of epsilon delta dp guarantees into hypothesis testing interpretation. So when we do that, we can actually show that the plots improve a little bit. So we get the yellow lines, which are closer to the red. But still, the gap is very large. So I don't think this contradicts the analysis of the paper in any way. It's just that by leveraging this property that we can evaluate epsilon delta guarantees for many deltas, we can get slightly improved plots, but these plots still show like a very big gap. So where else can the gap come from? And here is where I think really like this result that shows that when you're doing amplification by subsampling using FDP, you can get like this huge gray area of difference between just what the blue curve does, which is just the subsampling result for standard epsilon and delta, and this red CP that I have to admit that I follow the derivation like all the steps, but I don't have a very good intuition of why this big gap exists. So I would really like to understand that. One thing that might be happening, I'm not exactly sure, is that when we look at amplification by subsampling for a standard, say, epsilon delta dp or even epsilon dp, there is a phase transition. So here in this plot in the right, what I'm showing is epsilon, say the original epsilon of a mechanism on the x-axis, and on the y-axis, different final epsilons for a subsampled mechanism. And the blue curve in the right plot is actually like what also corresponds to the blue curve on the left plot. And we see that when the original mechanism has like very small epsilon, the amplified privacy kind of follows like p or eta times epsilon, so it's very low. But then as epsilon increases, there's some phase transition and we stop getting amplification. So I think that might be one possible thing that is happening here. But I'm not sure. So I was hoping the authors later can be able to answer that. And to conclude the vote of thanks, I also wanted to look at this last paragraph of the conclusion that I liked a lot, which basically says that ultimately the test of a privacy definition lies not just in its power and semantics, but also in its ability to analyze useful and diverse algorithms. And basically, I wanted to propose a challenge to show that GDP can really analyze like a much wider diversity of algorithms than other definitions do, or at least like do so in a tight way. So the challenge would be to take the standard noisy SGD, which usually we write in this way, where the main important point here is that when we take the data set at each iteration, we subsample at random. But this is not how this is really implemented in practice. In practice, what happens is that instead of subsampling at random at each iteration, what we do is at the start of each epoch, we apply a random shuffle to the data set. And then during that epoch, we take consecutive batches of M examples at each iteration. So I think it will be really interesting to see if GDP can also provide us with the tight analysis of this algorithm. And the challenge here is that now the randomness in the mechanisms is not going to be independent anymore because the shuffling introduces some correlations. And maybe what would be needed here is some form of CLT for weakly dependent random variables in this GDP form that the authors showed us earlier. So that's all. That concludes my vote of thanks. I just want to congratulate the authors again for a very nice paper.
Okay, thank you very much, Borja. If you could unshare your screen. And I would now like to call on Marco Avella Medina from Columbia University to second the vote of thanks.
I wanted to thank the authors for a very nice paper, and the organizers of this discussion for giving me the opportunity to comment on this. And I'm also supposed to challenge some aspects of it, at least a little bit. So let's see how that goes. I wanted to start first by overviewing some of the results presented in the paper in various different sections of the paper, and this, of course, very simplified. But there's many interesting and sort of elegant deep results in every single section. And perhaps for starters, this has been mentioned already that if we compute a statistic for which we can bound its sensitivity in the sense of the worst possible change of this statistic, we change only one observation, then that's the global sensitivity, then this is one way of obtaining a differentially private output. And one of the nice things that the authors provide is a clean interpretation of what this actually means, and they frame it in the context of hypothesis testing, when it becomes the question of whether we can distinguish two Gaussians. So this is certainly very nice. Then they have a very elegant characterization of composition, which for the particular case of Gaussian differential privacy means that if we have capital K, I change in the notation from the authors I used, and if we have capital K, Gaussian differentially private mechanism, if we compose them, then it becomes simply a product, and we can characterize very tightly, precisely what the resulting privacy guarantee is. And there is more to it. There is some sort of sense of universality of this result, in the sense that if we compose many F differential privacy mechanisms, they're going to be approximately following a Gaussian differential privacy guarantee. And finally, as they have also pointed out, so Borja just did, there's this idea of privacy amplification via subsampling that is further enlightened by the author's effort. And in particular, they characterize it by introducing this subsampling operator that tells us that if we have some algorithm that is f-dp, then if we subsample, we can characterize its differential privacy guarantee now by an operator that acts on the original f that we have in the f-dp definition that was satisfied by our original algorithm. So if we do subsampling, we can characterize somehow in what sense we gain more privacy, and this can also be extended to scenarios where we are interested in composition. And I wanted also to remember all of this, because all of these play a role in the stochastic gradient descent algorithm that I copied from the paper, and it's going to be the main focus of my discussion. And I want to focus on this by framing it more in a context of parametric statistics. So just to refresh the notation, we have a loss function L, and we have n data points. What we do to get our estimator is to run gradient descent, but instead of simply evaluating the gradient at every single point. We compute a random subsample at each iteration of the gradient descent algorithm, and we do so not on the pure gradients of the loss function, but on a clipped version of that, and we add noise to it. So there's a few tuning parameters here. Here, the number of iterations that we set beforehand for our gradient descent, the clipping parameter that we're using to sort of bound the gradient of our loss function, and the privacy inducing noise that is going to be related to the final privacy guarantee that we want to have. Okay, so many of the questions we can ask can be related to these things that I mentioned, and I would like to in particular talk about how do we choose the clipping constant, whether we can say something about the convergence of the algorithm to a solution, and whether we can say something about the statistical properties of the final output of this algorithm. And I'm going to give at least some partial answers to this by using some connections, mentioning some connections to M estimators and robust statistics, in particular to think of the clipping constant. And I'm gonna be mixing these points 2 and 3, give some ideas from classical stochastic gradient descent before we discuss the noisy one, and discuss some consistency result for a noisy full gradient descent as opposed to the stochastic one that is proposed by the authors. So one of the connections that we can make to robust statistics is to think simply about the objective function that would be, or about the estimator that we would be computing if we are not running stochastic gradient descent, but rather evaluate really the full gradient and keep on iterating. We can define an M estimator, so the solution to an equation of this form, if we have L of f being the log likelihood, and the clipping operation, what it does, it bounds this gradient, this individual log derivative of the log likelihood, using a function that in the context of robust statistics is called multivariate Huber function. And this is interesting because it gives us some sort of perspective as to what are the statistical properties of a parametric estimator that solves this equation, at least in an IID setting, for example. And if we think of least squares and we simply apply this clipping function, then in fact, we can think of the properties of this, and unless we have that this score equation is unbiased in the sense that the expectation under the model that generates our data equals 0 here, then they will not have consistency, which is something we'd have to think about when it comes to the clipping constant. There's way to remedy this, for example, taking a divergent clipping constant, but then we would add more noise to the private algorithm. But there's alternatives to it. And for example, in robust statistics, something that we can do is to apply the Huber psi function just to the residuals here, and to downweight the x's by dividing by their norm, for instance, and this would be called a Huber estimator of the Mallows type, and this one is indeed consistent. Okay, but the question remains, how do we evaluate this? And for that, I'm going to talk about an even-simpler case. I'm just going to consider a Gaussian IID setting, and I'm trying to estimate this parameter theta by a Huber estimator, and I'm running plain gradient descent and noisy gradient descent. So I'm adding noise to the gradient of the Huber loss, and we see what happens. So the non-noisy gradient descent, so the non-private one, is this black line, and we see that we have some random iterations around this non-noisy gradient for various sample sizes. As the sample size increases, we're getting closer to that non-noisy gradient because we add less noise. And I marked this line here 10 in the sense that this red line was set to satisfy differential 1 Gaussian differential privacy for 10 iterations. So this is sort of one of the tuning parameters, and our final estimate would be the value of the red line at this particular point. You can question what happens if we actually schedule 40 iterations instead, and you do see an increase of the variance noise to get to the same privacy guarantee. That is because we want to schedule more iterations. And you do somehow, however, feel that while we add more noise, it is not terrible, at least not compared to the amount of maybe bias that is generated by the correlations in this subsequent iteration. So one might wonder at some point if it is worth actually adding more noise to your algorithm, iterating more, and perhaps figure out a way to use this additional information that you would have between this red and this blue line if we were to schedule more updates. There is something we can say, sort of theoretically, this is something I have, it's ongoing work with Casey Bradshaw, a PhD student at Columbia, and Pauline Lowe, and that we have been trying to understand. And it's noisy gradient descent. So it's not a stochastic version because we have a full gradient evaluation and we have an M estimator. So this would be the derivative of the log likelihood if we are in the likelihood setting, or the derivative of some robust loss that we assume is bounded. That's why this soup over here makes sense. And this means that the M estimator that we're picking has a bounded influence function. This would be the sense of it from the robust statistics perspective. Oops, I left this by mistake. Then we can actually say something about this algorithm. In fact, under local strong convexity, we have shown that it suffices to take log n steps to guarantee the following, that the final output is mu Gaussian differential privacy. This follows from the results of the paper. Perhaps more interestingly, we are fairly close to the non-private estimate up to a noise that is directly coming from the magnitude of the noise that we add to each gradient step, which means that provided we don't take too many iterates, this term would not be dominated by the statistical noise. So the statistical noise is strictly larger than this one. And from that quick remark, we can see that in fact we have asymptotic normality of the following, of the resulting estimator if we run gradient descent. So one can wonder then what happens if you take a stochastic gradient descent. And I'm being a little bit slow, so I'm going to try to speed up a little bit and just remind briefly that stochastic gradient descent is known to converge slower than gradient descent. And we're showing here what happens in the non-private setting. And we have gradient descent here evaluated in terms of how the solution is converging to the true parameter, which here was said to be 1. Or if we want to look at the absolute value of the gradient should go down to 0. And we do see that the gradient descent algorithm goes down to 0 very fast, while the stochastic gradient descent algorithm do converge slower, and larger mini batch size makes this convergence go a bit faster, but still there is something fundamentally different in the behavior of these two algorithms. And this was supposed to be on a log scale of the gradient. So some problems that I might see if we think of now the statistical properties of the estimator that results from a stochastic gradient descent algorithm, if we care about things like asymptotic normality of that estimator, or consistency of that estimator, for example, are the following. So standard stochastic gradient descent, as I said, converges slower than gradient descent, and also perhaps more fundamentally, a smaller mini batch size will lead to a larger privacy noise that we will need to add to our algorithm. And as I saw in this previous result, if we add more noise to this term, that would blow up this term, and this might be at odds with the desired statistical properties that we might like for our stochastic gradient descent, again, if we care about parameter estimation. Okay, and some high-level ideas of what might be going on is that, borrowing from knowledge from classical optimization theory, the fundamental difference in the convergence properties of gradient descent and stochastic gradient descent is that, in a sense, the gradient descent converges exponentially fast to 0. We have gamma constant between 0 and 1, whereas stochastic gradient descent converges slower. This is not too bad, but it can be dramatically improved if you take more sophisticated versions of stochastic gradient descent, such as variance reduced approaches. So that might be one way to go. However, small mini batch sizes would still lead to large privacy-inducing noise. So we have to think about how to think of that. And because I'm running out of time, I will just say that this fast convergence is what explains why we only need log n terms for noisy gradient descent to converge pretty fast. And it's a little bit unclear what happens if we take stochastic gradient descent. If I stop at one more picture, I go back one slide, the idea will be that noisy gradient descent varies randomly around the black line that I showed here, while stochastic gradient descent, noisy gradient descent would oscillate sort of randomly around the colored ones here, which are themselves just a slightly inferior benchmark for the estimate. So I want to stop there and just congratulate the authors for a very, very nice paper. I really enjoyed reading that again over the last weekend. Thank you.
Okay, thank you very much, Marco. So the vote of thanks has been proposed and seconded. Please can I ask people to mark their appreciation either using the clap hand emoji or indicating some other way. Got to find the clap hand emoji. Yeah, there you go. So this is a modern way of applause. Okay, I'm sure more will come up as people figure out where the emoji is. There we go. All right, I'd like to now move on to the discussion part of the meeting. And I would like to remind everybody, please keep your microphones and your cameras off unless you're speaking. We have one discussant who has already pre-identified. Discussants have a maximum of 5 minutes speaking time, which will then translate to up to 400 words in the journal after the meeting. So could I please call on Peter Kruski, who's from Novartis, to contribute to the discussion for 5 minutes, please.
I'm Peter Kruski. I work for Novartis in a group called Advanced Methodology in Data Science. And I was just going to, I guess, pose a few practical questions on the applications of differential privacy in the setting of pharma and clinical trials. The first slide I have for you is just a quick introduction of why are we interested as a pharmaceutical company in privacy, and what are our particular challenges that we face when we work with personal data and privacy. And to start with, pharmaceutical companies do very regularly collect personal data from our patients to conduct clinical trials. And we also have a strong need to share clinical data, or most prominently perhaps with regulators when we go for submission, or with committees that ensure the integrity of our trials. But typically this first phase is covered by consent by our patients that participate. But the second two are the more interesting ones, and these actually are the ones that would enable us to contribute also our data towards sort of the scientific progress and understanding of disease. So the first scenario is one where we might want to share data with academic collaborators. The second one is where we want to summarize data for internal research and, for example, bringing most of our data together and performing secondary research on our clinical trials internally. And for both of those scenarios, it's actually critical to ensure that we respect the patient consent and limit the risk to the patients through data disclosure. So how does this kind of interact with differential privacy? So the first one is kind of more of a challenge that we encountered when we looked into differential privacy for implementing that. And I guess I'd be curious to hear the thoughts that you have on that, and how this might move forward practically as well as theoretically. So that is that a clinical trial, differently perhaps from real-world evidence data, where I know that differential privacy is also being applied, typically consists of hundreds of thousands of patients, and collecting data on those patients is very expensive. So running a clinical trial might cost something in the tens or 50 millions of dollars, and then we have data on 1,000 patients that we may need to summarize. And for such small participant counts, it's actually quite hard to choose an epsilon or an epsilon and a delta that actually gets us a sort of a reasonable approximation of the answer while still guaranteeing privacy. I guess my first question is, would that be something where you could see a material improvement when picking instead a mu through Gaussian differential privacy? The second challenge is one that also kind of relates to this first one, where we have only small numbers of patients, and once we publish a summary on those patients using a certain budget of privacy, then that budget is gone. So we may actually, for a complex set of summaries, want to optimize how we spend that to balance requirements for accuracy with requirements for privacy. And again, one thought I had that might lead perhaps to also applications in our field would be, could we use particularly the concept of f-differential privacy to optimize the privacy budget more intelligently, rather than just parameter sweeping across assigning epsilons to different steps of an analysis. So those are my two thoughts. Overall, I'd really like to thank the authors for sharing the paper and for the great presentation earlier. I really think it's improved my understanding of the field substantially. And also thank you for the opportunity to speak here.
Okay, thank you very much. Before I move on to the next section, I would like at this point to invite any contributions from the floor. If you do wish to contribute to the discussion, please indicate in the chat or raise your hand and we will come to you. Okay, I see no hand or anything extra in the chat. So I will now call on the Honorary Secretary to read the two written contributions that we have received at this point.
Yes, thank you, Guy. So we've received two contributions. The first contribution is from Dr. Christine Chai from the Microsoft Corporation. And she says, since the authors used subsampling to amplify privacy guarantees, I wonder if they have considered moving to fully synthetic data to preserve perfect privacy for all individuals. This way, individuals cannot be identified from the synthetic data because the data do not contain real people. Can the hypothesis testing framework be applied on proving that the synthetic data have the same key statistical properties as the original one? Another question I have is how Gaussian differential privacy preserves data's usability. The paper discussed the trade-off in terms of type 1 and type 2 errors from the attacker's perspective. So I'm curious about the trade-off between privacy guarantees and data usability, that is, the privacy budget. Researchers have expressed concerns about the accuracy of census public release data due to the implementation of differential privacy and disclosure avoidance methods. Last but not least, would the proposed Gaussian differential privacy framework apply to COVID-19 contact tracing data in the future? Do the authors anticipate any major challenges in the implementation? So this was the first contribution. We've received another contribution from Sebastian Dietz from Munich. The remarkable new contribution is the usage of trade-off functions between error types 1 and 2, which leads to the generalization of differential privacy. It is intuitively well visualized by a kind of inverse ROC. Via central limit theorem, theorem 4, it is shown that a tensor product of symmetric trade-off functions with finite first to third moment is bounded by a Gaussian trade-off function. The proof in section D incorporates the classical Berry-Esseen theorem as theorem D4. Shortly in section 3.2, the topic of requirements of a finite third moment is touched, which is crucial for the Berry-Esseen central limit theorems. For transferring the results of the dp central limit theorem to epsilon delta dp, there the question is taken up again to prove convergence to a Gaussian trade-off function in section 3.3. In the literature, some generalizations of Berry-Esseen exist. See, for example, Petrov 1975, where theorem 5 states in a simplified form. So a theorem is stated, a Berry-Esseen theorem that only requires a moment less than order 3. Using such a third moment free central limit theorem, the epsilon delta dp trade-off function could also be covered by the central limit theorem, as well as a potentially larger scope of trade-off functions. The proof do not require specific value for the constants, such that a consideration of this Bayesian extension might be an option, whereas handling of G might be a limiting issue. That's it.
Thank you, Christoph. I would now like to offer to the authors an opportunity to reply if they wish. You have up to 10 minutes. You don't have to fill the 10 minutes, but you have up to 10 minutes. And of course, reminding you that you have the opportunity to give a more considered reply in the journal in due course. So over to you, authors.
First of all, Jinshuo, Aaron, and I would like to thank everybody very much for your very insightful and sharp comments. And so while we will, of course, respond to them in detail in our written in our response published in the journal, and we will also take maybe the next 10 minutes to say something about to some of the questions. Yeah, I think Jinshuo will handle maybe most of the questions, but I can briefly talk about a question raised by Borja in his slides, asking why there is a dramatic gap between the privacy analysis of GDP using the privacy analysis of SGD using GDP and Renyi differential privacy. So actually, he had identified one of the reasons. One reason is that in Jinshuo's plot, we are only showing a single instance of epsilon delta. And so if you optimize over epsilon delta, essentially you plot the envelope of different epsilon delta curves. You can certainly improve. You can reduce the gap between GDP and the Renyi DP, of course. And but there's another issue that I think I can only explain by going to their original paper. But would you mind sharing the screen? So let me share the screen. So this is the Ilia's original paper, which proposed the Renyi differential privacy. So this proposition, which translates the RDP guarantee to epsilon delta DP guarantee. So essentially this says that if a method is alpha epsilon RDP, then this is also epsilon delta DP with this pair of epsilon and the delta. But this translation is lossy. It will lose something. In particular, if you go in detail to their proofs, so you will see that there are several strict inequalities which made the analysis less sharp. So this is, this is from a theoretical perspective, and yeah, maybe it's possible to improve the translation better from RDP to epsilon delta DP. It's possible, but at this moment, I don't see how to improve it. And so, Jinshuo, do you have other things to add?
I think that explanation is precise. I personally believe. I think Borja mentioned a few problems. One is why amplification, like our amplification theorem, has such a large gap with the previous one, and that is explained by the, if you are epsilon delta DP, you're not only epsilon delta DP, you are epsilon prime delta prime DP simultaneously. So you can also amplify that. After that amplification, you consider all the amplification simultaneously, you actually get our theorem. Yeah, and about Renyi, I I still don't precisely understand how much it loses by doing a conversion Avella or F to DP and then back. But we do have an example that it is lossy. That is not equal, but how much larger going one way, going one way to the other direction is we don't quite understand.
Okay, thank you, authors. And thank you very much for your reply. As I said, you can have obviously an opportunity to reply more in the journal in due course when you've had a chance to think things over. So it just remains my final duty to tell you about the next discussion meeting. I don't have any details of a specific one, but just to say upcoming discussion meetings will be available on the RSS website and announced in our Stats Life and members newsletters. And if you want to be informed personally about all future discussion meetings, there is an email address, journal@rss.org.uk, and you can be added to a distribution list. So thank you very much, everybody, for attending. Thank you very much, speakers, the authors, the proposer, the seconder, and the discussant, and also the honorary secretary for reading out two of the discussion contributions. So all the best for the festive season coming up. And can I wish you a happy and successful and healthy 2021.